Hey everybody, how are you all doing? So in this stream we are going to review notebook 8 of FastAI course. It contains collaborative filtering. I have gone through the video walkthrough of the course. So we are going to go into the details of what each of the code means. So let's get started then. Collaborative filtering deep dive. So one very common problem to solve is when you have a number of users and a number of products and you want to recommend which products are likely to be useful for users. And there are many variations of this. For example, recommending movies such as Netflix, figuring out what to highlight for a user on a home page, deciding what stories to show in a social media feed. The Restream chat application I'm using is a little bit buggy. It sometimes doesn't display and it becomes transparent. Let me change the notification settings. I want to enable the desktop notification, right? And the window should remain always on the top. Cool. Let me move it aside now. Cool. Let's get back to the notebook now. Okay, so I was reading. There are many variations of this. For example, recommending movies such as on Netflix, figuring out what to highlight for a user on a home page. Okay, deciding what stories to show in a social media feed and so forth. Also recommending videos for the YouTube, this recommendations. That's also one of the application of collaborative filtering. There is a general solution to this problem called collaborative filtering, which works like this. Look at what products the current user has used or liked. Find other users that have used or liked similar products and then recommend other products that those users have used or liked. Alright. For example, on Netflix, you may have watched lots of movies that are science fiction, full of action, and were made in the 1970s. I think the whole Google ecosystem, which includes YouTube and Google search results and all that, has become very much intelligent at recommending stuff. Like it knows exactly what you want. Like it knows more about you than you know about yourself. And thinks it works across the content, like it matches different content. Like if you are watching fitness and different movies as well, it will connect all those variables. It has become so much intelligent. Okay, that aside, let's move on. that used like similar products and recommended. For example, on Netflix, you may have watched a lot of science fiction full of action and were made in 1970s. Netflix may not know this particular properties of the films you have watched, but it will be able to see that other people that have watched the same movies that you have watched also tended to watch other movies that are science fiction full of action and were made in the 70s. Okay, so Netflix AI doesn't know particular properties of the film. I think Netflix uses a hybrid approach. It does use particular properties. I don't know. That's real. In other words, to use this approach, we don't necessarily need to know anything about the movies except who like to watch them. So, in essence, people who watch this also like to watch this. So, if you are in that group, you will also like these things. That's the basic logic. Okay. There's actually a more general class of problems that this approach can solve, not necessarily involving users and products. Indeed, for collaborative filtering, we more commonly refer to items rather than products. Items could be links that people click on. Okay, links that people click on. So the people who click on this links predict what other links they might click on next, predicting what their action will be next. Okay. Diagnoses that are selected for patients and so forth. So key. So the idea is, I guess, predicting the next action the user should take based on what other people like this user has taken in the previous examples, previous cases, I should say. Right. The key foundational idea is that of latent factor. Latent factor. Okay. In the Netflix example, we started with the assumption that you like old action-packed sci-fi movies. Old action-packed sci-fi, but you never actually told Netflix that you like this kind of movies, and Netflix never actually needed to add column to its movies table saying which movies are of these types. I think it does include the columns. Like there are these genres which includes, like sci-fi, horror. So it must be using a hybrid approach. Still, there must be some underlying concept of sci-fi, action, and movie age. Okay, so it's also it seems that Netflix also uses, the explicit explicit categories, and also it must be deriving the implicit categories from the data, like science, this underlying concept of sci-fi, action, VH, and these concepts must be relevant for at least some people's movie watching decision. Like if I like to watch heist movies, then recommend me more heist movies and TV shows. Uh, I think there was one cool site which showed something like that, similar movie or something. Let me find that website. Similar movie. Well, I'm gonna leave it for now. I don't seem to remember the name of the website. For this chapter, we are going to work on this movie recommendation problem. We will start by getting some suitable data for collaborative filtering model. First, look at the data. We do not have access to Netflix entire data set of movie watching history, but there is a great data set we can use called movie lens. This dataset contains tens of millions of movie rankings, a combination of movie ID, a user ID, and a numeric rating. Although we will use a subset of 100,000 of them for our example. If you are interested, it would be a great learning project to try and replicate this approach on the full 25 million recommendation data. 25 million, which you can get from their website. I think as it is not image dataset, don't be that much slower as compared to image dataset, image recognition and all that. Okay, let's get the data now. I'm gonna copy the code directly. According to readme, the main table is in the file udata. It is tab separated and columns are respectively and the columns are respectively user, movie, rating and timestamp. Since those names are not encoded, we need to indicate them when reading the file with pandas. Here is a way to open it. Right, we have to use the pandas library. We'll get it inside the ratings variable. Let's use pandas read CSV function, and we have to provide the path and it should be u.data, which contains the data. Delimiter or delimiter, whatever it is called, is tab. So it is named comma separated values, but this CSV ironically contains the tab separated value, not comma separated value. Header is equal to null. Okay, so this CSV doesn't contain the header by default, therefore we are providing header equal to null, and I have to provide the names. So first column is user, second column is movie, third column is rating, and timestamp the fourth column. Let's display the view of the lines from the beginning of the data frame using the dot head. What's the rating is not defined. I don't mean it is not defined. Not defining anyway. I don't need to define it. Have I missed a comma or something somewhere? Oh yeah, shit. It is not rating, it is rating. Silly me. User movie rating. Okay, we have got the data frame now. It contains user ID or movie ID, the rating that this particular user gave for this movie, and the timestamp. Okay, what exactly is this timestamp? Is it the date? Does it contain the age of that movie, or find it out? Let's check the movie lens web page. I don't want to open it in this tab. I want to open it in new tab. Now we are going to have to reload the notebook. GitHub is very much slow in terms of loading the Jupyter notebooks. They are not Jupyter notebooks, just notebooks. This time it is taking a lot of time. Is that the case? Cool. It's being reloaded now. I want to open the movie lens website in a new tab. Movie lens readme.txt. Timestamp. Here it is. Timestamps represent seconds since midnight. Okay, but for what? What does it really represent? Is it the age? No, it can't be the age. Okay, it doesn't matter. Don't need to know. I guess we are not going to use that column anyway. So let's leave it for now. Okay, although this has all the information we need, it is not particularly helpful for humans to look at this data. It's not very convenient to check what how much rating a particular user has given to all the movies in this kind of table. So we need this kind of table where we can select a particular user and check across the row how many ratings, how much rating that particular user has given to all the different movies. Cool. We can also check a particular movie and check how many reviews it has got from all the users. We have selected just a few of the most popular movies. Users who watch the most movies for this cross tab example. Okay, the empty cells in this table are the things that we would like our model to learn to fill in. So these are the values that we want to predict. So for this user, we want to predict if that particular user is going to, how much rating that particular user is going to give to this movie, and for this movie as well, and so on for all the empty values. and that way we can know that if he or she is going to like that movie or not. And if the number is higher, well, that's for later. First the task is to fill these values. The empty cells, okay, those are the places where a user has not reviewed a movie. Okay, you get it? Presumably because they have not watched it. For each user we would like to figure out which of those movies they might be most likely to watch. So out of all the missing values for that user, we have to find which of the movies that user might rate as the highest, and we want to, and that basically corresponds to most likely to watch, most likely to enjoy as well. If we know for each user to what degree they liked each important category that a movie might fall into, such as genre, age, preferred directors and actors, and so forth, we knew the same information about each movie. Wait, what is it trying to say? If we knew for each user to what degree they liked each category, each important category that a movie might fall into, okay, such as genre, age, preferred directors and actors, and so forth, we knew the same information about each movie, and we knew the same information about each movie. And a simple way to fill in this table would be to multiply this information together for each movie and use a combination. For instance, assuming this factor range from -1 to +1 with positive numbers indicating stronger matches and negative number weaker ones, and the categories are science fiction, action and old movies, and we could represent a movie The Last Skywalker as alright. So this are we can say the latent factors. These are the latent factors. So we are not explicitly saying that the first number is for science fiction, the second for action, and third for old movies. We're just saying that assuming these factors range, we're just assuming that those factors range from -1 to +1. And we select, say, let's say 3 numbers or 3 latent factors, and we provide 0.98.9 -0.9 for Life Skywalker. So this is the one we are deliberately providing. Deliberately is not the right word. We are what can I say, we are manually providing. These are the values that we are manually providing. As a person, we know that Last Skywalker, it's for these 3 categories: science fiction, action and old movie. It is a science fiction, so we are going to give it greater value, almost close to 1.9, because it also contains action and old movies. Last Skywalker is the newest one, I guess, right? It is from 2019, so yeah, it is not old movies, so that's why we are giving negative value for old movies factor. And here, for instance, we are scoring very science fiction as 0.9. Okay, That's what I said. We could represent a user who likes science fiction movies as modern science fiction movies. So now we are also providing values for users who like science fiction. So this much he likes science fiction, this much he likes action, and this much he likes old movies. So he doesn't like it very much. So that's why we have given negative value. If we multiply both of this, so let's copy the code. Last Skywalker and user. Now we multiply both of those. Last Skywalker. So this will do the element wise multiplication. This will multiply 0.9 with 0.98 and 0.8 with 0.9 and so on. And finally we will sum the values. It will give us 2.1. Suppose all of these values were, wait, what is this particular number represents? When we multiply two vectors together and add up the result, this is known as the dot product. Okay, it is used a lot in machine learning and forms the basis of matrix multiplication. We will be looking at a lot more at matrix multiplication and dot products. Dot product, the mathematical operation of multiplying the elements of two vectors together and summing up the result. On the other hand, we might represent the movie Casablanca as this. So it's not science fiction. It's not that doesn't contain that much action, but it is old. And if we multiply that movie, let me copy that movie. Now if we multiply that movie with our user one, which we described over here, Casablanca, then we get a value which is very close to negative, means the value is negative. So if the value is negative, it represents that this user doesn't like this kind of movies, right? Since we don't know what the latent factors actually are, we don't know how to score them for each user in a movie. We should learn them. Who's the criminal? Am I the criminal? Why am I the criminal? right? Since we don't know what the latent factors actually are. Okay, so we don't know the latent factors like science fiction, action, and old movies and so on. And also we don't know how to score them for each user and movie. So we should learn them. Okay. So these are the factors that we are going to, somehow produce with computation. Alright, so let's learn how to get those factors, latent factors. There is surprisingly little difference between specifying the structure of the model as we did in the last section and learning one. Little difference, since we can just use our general gradient descent approach. There is surprisingly little difference between specifying the structure of a model. Okay, as we did in the last section, and learning one, since we can just use our general gradient descent approach. Okay, that means he's talking about the structure, specifying the structure. Step one of this approach is to randomly initialize some parameters. So in this case, we are assuming there are in total 5 latent factors and initialize those randomly. Alright. And these parameters will be a set of latent factors for each user and movie. We will have to decide how many to use. We will discuss how to select these shortly, but for illustrative purposes, let's use 5 for now. Okay, because each user will have a set of these factors and each movie will have a set of these factors, we can show this randomly initialized value right next to the users and movies in our crosstrack. Because we will discuss how to select. Okay, because each user will have a set of these factors and each movie will have a set of these factors, we can show this randomly initialized value right next to the users and movies in our crosstrack. Okay, and we can fill in the dot products for each of this combination in the middle. Oh, cool. So dot product of this versus this will reside in this particular cell. Step 2 of this approach is to calculate our prediction. Just to calculate our prediction, what does it mean? Okay, calculate this prediction. As we have discussed, we can do this by simply taking the dot products of each movie with each user. If, for instance, the first latent user factor represents how much the user likes action movies, the first latent movie factor represents if the movie has a lot of action or not. The product of those will be particularly high. If either the user likes action movies and the movie has a lot of action in it, or the user doesn't like action movies and movies doesn't have action in it, okay, so it will also be high for the case where the user doesn't like the movie and the movie doesn't have any action in it. So for, let's say, this kind of case where the last Skywalker is not old and this user doesn't like old movies as well, so the product of this will be positive and it will be higher as well. So the more old the movies, more older the movies, and the more negative this rating for that user, the more negative this number for this user, the higher the sum will be. So it not only predicts what you like, it also predicts what you don't like and heightens it. Cool. Was I? Okay. On the other hand, if we have a mismatch, a user loves action movies but the movie isn't an action film, the user doesn't like action movies and it is fun, then the product will be lower. So suppose this user likes old movies, so that means this number will be much higher and it won't be negative, it will be positive. And if it is multiplied with last Skywalker, then it will sorry, what I want to say, if I multiply 0.6 with minus 0.9, then the number will be higher and more negative. So suppose the user likes a lot, if the rating for older movies is a lot, in this case, suppose if it is close to 9, this movie is very much newer, so it is close to -9. In that case, again the number will go very much higher, negative, and this will reflect, this will affect all other values as well, because this will be subtracted from the previous dot products. So this will have an effect and it will lower the score for that particular movie for that user. Okay, I think I get it. Okay. Step 3 is calculate our loss. Okay, so after we have calculated the prediction based on these values, now we want to calculate the loss. You can use loss function that way ways. Let's pick mean squared error for now, since that one is a reasonable way to represent the accuracy of a prediction. Mean squared error. Okay, that's all we need. With this in place, we can optimize our parameters, that is the latent factors, using stochastic gradient descent, such as to minimize the loss. At each step, the stochastic gradient descent optimizer will calculate a match between each movie and each user using the dot products, and will compare it to the actual rating that each user gave to each movie. It will then calculate the derivative of this value and will stack the weights by multiplying this by the learning rate. Okay, after doing this lots of times, the loss will get better and better, and the recommendation will also get better and better. To use the usual learner.fit function, we will need to get our data into a data loader. So let's focus on that now. Right, let's get the data loaders now. And showing the data, we would rather see movie titles than their IDs here. And the table u.item contains the correspondence of IDs to titles. Alright, so the corresponding titles to the IDs is inside uItem. So let's get it into the data frame as well. And also read CSV. Let's provide the path, and we want to select u.item. Delimiter, it's again tab. Wait, in this case it is vertical line, whatever this is called. What is it called anyway? Vertical bar. Okay, so in this case the delimiter is the vertical bar, and encoding is done in Latin. Okay, we have to provide encoding as well. Latin. What is that? Use columns. What does this use column do? Use call. Let me check the documentation. Read CSV. Does use calls do? Use calls list returns a subset of the column. Okay, it returns the subset. Okay, so this use columns will select the first. So that mean u.item contains other columns as well. Maybe. So let's pass use calls and 0 and 1 to select first and second column. We have to provide the names for the headers as well. This time it will be a tuple. Previously we provided a list, movie and title. Finally we provide header is equal to none. And let's review the header of the data frame. Okay, we have got the data frame now. We have got the movies. Although this column, I guess, is it necessary to have this column? But for the first few, let me select a random sample and check if the movies are just returns one. I want 10 samples. Okay, so the movies are not ordered and the IDs are not, sequential. So yeah, we do need this index column. It is sequential because the indexes and then movie IDs are corresponds perfectly. It doesn't matter. Let's go back to head. We can merge this our ratings table. Okay, now we want to merge this with our rating tables. So rating table contains a movie ID and this table contains movie IDs as well. So replace we want to merge based on this movie IDs, which is the common column for both of this data frame, and we want to replace it with title, right? uh, we can keep the title as we can keep the movie ID as well. I guess we have a convenient function named merge, so we will be uh, saving the result in the ratings table. Want to merge ratings with movies, so I guess it will automatically select the common because this table contains movies and this table contains movie. So how is it going to know that which is the common column? We should check out the documentation. Now in on left, none, right object to merge with, and how inner. So the default is inner, and what does it do? Use intersection of the keys from both frames, similar to SQL join. Preserve the order of the left keys. Okay, so it seems that it selects The last column, is it the last column? But the movie is it the last column? Is it going to decide on which column it should on none column or index level of names to join, and this must be found in both data frames. If on is none and not merging on indexing, that this default to the intersection of the columns in both data frames. Don't get it. So we are not providing any other values, we are just providing right, which is movies, and the house inner by default. Everything else is none. Left index is false. We are not even providing on. We are not even providing column or index even to join on. df1 with df2 on A. Four, 1, 4, 3, bar 2, bars 4. Okay, so if I provide on is equal to A, then it will get rid of this column, this row. It will only find the column which are intersecting. So this is intersecting with this, so that's why it will keep only this row. In this case, they have provided left. So in this case, okay, so left, if left is provided, then we don't get rid of the rows from the left side, from the left data frame, but we get rid of the not common row from the right data frame. But I don't get it. How does it know that this column movie and movies is similar? Merge movies. Let's merge movies and let's check the results. 10 samples. Get 5 samples. No common columns to merge on. Exactly, that's what I'm saying. Okay, so it seems we have made a typo over here. We were supposed to provide only movie. We provided movies. So that's why. So it does search for a common column name. So now it will search for the common column name. Okay, now it is clear. Now I get it how it works. Good, let's move on. Let's only get the head of it. Cool, yeah. We can then build a data loaders object from this table. By default, it takes the first column for the user, the second column for the item. Here are our movies. First column, the third column for the ratings. We need to change the value of item name, in our case, to use the titles instead of IDs. Okay, so we can use collab data loaders. DLS collab data loaders from data frame ratings item name. So the item name is title, value of item name. We have user column by default in our data frame, so it will take that first column and second column for item. But item, we don't have a column named item, we have a column named basically we want the titles as the item, so we have to provide the item name over here, BS64. So batch size is equal to 64. Let's display the batch using the show batch method. Alright, we have got the data frame now. We have got the users and the title and the ratings. And this is one batch of it. Now to represent collaborative filtering in PyTorch, we can't just use the cross-track representation directly, especially if we want it to fit into a deep learning framework. We can represent so where was I? We can't just use the cross-tab representation. We can represent our movies and user latent factors tables as simple matrices. DLS classes. Check my internet speed. the speed is good enough. So DLS data loader classes contains user and a title. Users NA. What is the name? 1, 2, 3, 4, 5, and the titles. That's what we have inside that classes. To fit this classes inside the PyTorch library, we have to create something like this. So we're getting length inside number of users. Okay, but this users also contains NA and a label. We surely don't need this label, right? Let's see how they tackle it. So we get it inside end user for DLS classes, and we select user. We do the same thing, but this time we select titles, the number of movies. Cool. And the number of factors, we are selecting 5. So this is the number of latent factors, user factors. So the users factor will be torch.random will be number of user factors. What does it take? It takes a size. It returns a tensor filled with random numbers from a normal distribution. Okay, get it, but let me first implement the code, then we will check the output. We are providing number of users. It should be users. Number of user and number of factors to torch.random, and number of movies let's also check the shape of user factors. It is 944 into 5. Okay, we are getting this number of random values. So we are basically doing, we are taking number of users. These are the number of users. Suppose these are 15, 10 or 15 users. Suppose these are 10 users, and the number of factors are 5. So we multiply it by 10, 5. Do we multiply it by, we get we want a matrices with rows same as the users, number of users. So this is the number of rows, and this is the number of columns, 5 columns, and we want a matrices filled with random numbers which has this dimension for rows and this number of columns. I get it now. So the total number of users are 944, and the total number of, let's also check movie factors. We don't want to display movie factors, we want to see it. has 1665 movies. Okay, now we have got the matrices. Now to calculate the result of a particular movie and a user combination, we have to look up the index of the movie in our movie latent factor matrix, and the index of the user in our user latent factor matrix. Then we can do our dot product between two latent factor vectors. Okay, they are trying to say we have to find this rating, we have to look up this latent factors and this latent factors, and then do the dot product. So we have to do lookup of this corresponding row and column, and they're saying that lookup in an index is not an operation our deep learning models know how to do. They know how to do matrix products and activation function. Fortunately, it turns out that we can represent lookup in an index as a matrix product. And how do we do that? The trick is to replace our indices with one hot encoded vector. Our indices, which indices are they talking about? Here's an example of what happens if we multiply a vector by one hot encoded vector representing the index 3. One hot 3 so we are getting a one hot encoded vector with this much size, which is a number of users, and we are providing 1 to 3rd index. Right, let's check. Let's display one hot 3. So yeah, the 3rd index is set as 1 and all of the other indices are 0, and the set will be same. I mean the size will be same as number of users, which is 944. Right, now if we multiply that one hot encoded vector with user factors, first we have to transpose it using T, and we do the matrix multiplication. First let's check what is inside user factor. Okay, so user factors contains this 945 by 5 matrices, 944 columns and 944 rows and 5 columns. Now if we transpose it, then it will be 5 columns and it will be 5 rows and 944 columns. Now we do the matrix multiplication, so this will be multiplied with 944. So there are 944 rows, 944 columns, and there will be 944 columns in one hot encoded matrix. So it will allow the matrix multiplication. If we do that, then it will only select, as we have 1 inside. Let me display it first of all. we have 1 inside this third index, then everything else will be zeroed out. For this row, everything else will be zeroed out. Only this number will be selected. Not this one, this is second index. The one after this will be selected. Selected means it will be preserved. Right, so it will be like this, and this multiplied, and this will become the first number. And same as for second row, and this one hot encoded, so it will basically give us total 5 values like this for this 5 rows, and it will only select this third column. So third column, so and that is exactly what we want, which is lookup. So this values will correspond to, suppose this is the third user, then those vector will be correspond to this values, the third indices of the user factors matrix, like this. So let's do the matrix multiplication, and if we could do matrix multiplication, we get this. Now if we do the lookup manually using selecting the third index of the user factors, we get the same thing. So basically we can do matrix multiplication with the one hot encoded vector and a transposed user factors and get the same lookup functionality. And as PyTorch can't do this lookup, but it can do matrix multiplication, we can provide the same functionality to PyTorch. Okay, now I get it. And if we do that for a few indices at once, we will have a matrix of one hot encoded vectors. Two indices. So they mean let's read on. It is saying that if we do that for a few indices at once, so not only we are selecting just one, if we select suppose more than one indice, so if this contains more than one ones, then it will select more than one numbers from this row corresponding to these ones. But I think that won't be that much useful. Let's read on what it is saying. This would be a perfectly acceptable way to build models using this kind of architecture, except that it would use a lot more memory and time than necessary. It is going to use memory because we are basically creating different vectors for this one hot encoded, for all the indices. So it will take a lot of memory. It will take space as well and it will take time to matrix multiply all those values as well. And we know that there is no real underlying reason to store the one hot encoded vector or to search through it to find the occurrence of the number 1. We should just be able to index into an array directly with an integer. Therefore, most deep learning libraries, including PyTorch, include a special layer that does just that. It indexes into a vector using an integer, but has its derivative calculated in such a way that it is identical to what it would have been if it had done a matrix multiplication on a hot encoded vector. This is called embedding. Alright, so we don't need to use this kind of function. PyTorch provides something which is called embedding, which provides the similar functionality, similar result as this. It indexes into a vector using an integer like this, I suppose, but has its derivative calculated in such a way that it is identical to what it would have been if it had done a matrix multiplication with a one hot encoded vector. This called embedding, multiplying by a one hot encoded matrix using the computational shortcut that it can be implemented by simply indexing directly. This is quite a fancy word for a very simple concept, the thing that you multiply the word hot encoded matrix by or using the computational shortcut index into or using the by. It's called the embedding matrix. In computer vision, we have a very easy way to get all the information of a pixel through its RGB values. Each pixel is colored image. In a colored image, it is represented by 3 numbers. Those three numbers give us the redness, the greenness, and the blueness, RGB values, which is enough to get our model to work afterward. For the problem at hand, we don't have the same easy way to characterize a user or a movie. There are probably relations for the problem at hand. We don't have the same easy way to characterize a user or a movie. There are probably relations with genres. If a given user likes romance, they are likely to give higher scores to romance movies. Other factors might be whether the movie is more action oriented versus heavy on dialogue, or the presence of a specific actor that a user might particularly like. How do we determine numbers to characterize those? The answer is we don't. We will let our model learn them. By analyzing the existing relations between users and movies, our model can figure out itself the features that seem important. This is incredible, how it does from just using simple computations. It gives the appearance of preferences of a user, like if it is a romance movie or not. It is incredible how this particular model works. There's a certain beauty to it. Okay, let's read on. How do we determine that numbers? Okay, how do we determine numbers to characterize those? Okay, we learn. This is what embeddings are. We will attribute to each of our users and each of our movies a random vector of certain length, here n factors, which in this case is phi factors. We have used phi latent factors in this model. So we are assuming that in this case we have 5 factors. We will make those learnable parameters. That means that each step, when we compute the loss by comparing our predictions to our targets, we will compute the gradients of the loss with respect to those embedding vectors and update them with the rules of SGD or another optimizer. At the beginning, those numbers don't mean anything. Okay. So initially they are all random, since we have chosen them randomly, but by the end of training they will. So this is what I call beautiful. So by the end of training, those apparently random values will turn into certain latent factors, which will be like, if this particular movie is, let's say, is in science fiction genre or not, and how much science fiction it is compared to other genre and all that. By the end of the training, those numbers will determine that. By learning on existing data about the relation between users and movies without having any other information, we'll see that they still get some important features and isolate blockbusters from independent cinema, action movies from romance, and so on. But the key thing is the initial data that we have, which we have. So from this initial data only, we'll be able to figure, the model will be able to figure out those latent factors from this initial data. From those numbers of the initial data, it can isolate blockbuster from independent cinema, action movies, and from romance, and so on. And we are now in a position that we can create our whole model from scratch. Okay, let's get to it then. Collaborative filtering from scratch. Before we can write a model in PyTorch, we first need to learn the basics of object-oriented, and Python. If you haven't done object-oriented programming, we'll give you introduction. The key idea is the class. We have been using classes throughout this book, such as data loader, string learner. Python also makes it easy for us to create classes. Okay, I get it. This is how we create a class. Here's an example of simple class. A dunder method init. Note that the first parameter to any method defined. Okay, we don't need to read it. We have provided this class. Also note that creating a PyTorch module requires inheriting from module. This is what we need to focus on. Creating a new PyTorch module requires inheriting from module. So this is how we inherit a module. Inherit the module, this module class. Inheritance is an important object-oriented concept that we will not discuss in detail. Okay, in short, it means that we can add additional behavior. PyTorch also provide a module class which provides some basic foundation that we want to build on. So we add the name of the superclass after the name of the class that we are defining as shown in the example. Final thing that you need to know to create a PyTorch module is that when module is called PyTorch, when your module is called, PyTorch will call a method in your class called forward. And will pass along to that any parameters that are included in the call. Here is the class defining our dot product model. Let's create the model class dot product, and we inherit the module class. It's also defined the under init method. First argument is self, second argument is number of users, third argument number of movies, fourth will be number of factors. We are also calling this embedding function, which embeds number of users with, okay, this embedding basically does this kind of thing. I think we should check it out what it does. It gives us 944 by 5, so it gives us this matrices. Let's copy these lines. Also need to provide the forward method self x. What does this x represents though? What is inside x? We're calling self that uses x, so apparently it's a list, it's a matrix. We are selecting. If you haven't seen object-oriented programming before, then you won't need it. You won't need to use it much. Let's just mention. Okay. Note that the input of the model is a tensor of shape, batch size into 2. Input of the model. At the first column, this selects the first column, contains the user IDs, and the second column contains the movie IDs. Batch size into 2. So in this case, batch size is 64. 64 is the default batch size, and to 128. Okay, tensor of shape. batch size into 2. Okay. This like 64 rows and 2 columns. 64 rows and 2 columns, and the first column contains the user IDs and the second column contains the movie IDs. Okay, now get it. So that's why we pass this. We select the from this user factors, as we are passing a matrices, only the first column. This will select the users, and we are passing second column, so this will select the movies. And finally we return users into movies.sum. I don't exactly know how this function works, but let's just roll with it for now, and maybe it will be clear later on. So now let's check the batch. So the shape of X is 64 into 2. So yeah, 64 rows and 2 columns. And let's also check what is the content of the X contains this. So these are the movies, and this are sorry, this first column contains the user IDs and second column contains the movie IDs. Okay, and let's also check Y. First check the shape of Y is 64 and 1. So this is just the rating factor. These are all the ratings. That we have defined our architecture and created our parameter matrices, we need to create a learner to optimize our model. In the past, we have used special functions such as CNN learner, which set up everything for us for a particular application. Since we are doing things from scratch here, we'll use the plain learner. So the dot product class gives us the model. Dot product. We pass the number of users to it and number of movies to it, and 50, which is the number of factors we are selecting in this particular case. And let's get the learner now. Learner, that's the data loader, the model, loss function. We are using the MS mean squared error loss function this time. And we have got the learner now. Oh, we can directly call the fit one cycle method. We will fit it for 5 epochs and pass 5 raised to minus 3 as the learning rate. Right, we are down to 0.72 loss for training and 0.86 for validation. The first thing we can do to make this model, this is just fit one cycle. So I guess this fit one cycle method will only find step the randomly added. Okay, yeah. Everything is randomly added because we are not using any. This time we are not using the transfer learning anyway, so there's no transfer learning happening. I have to get out of that, that concept for now. So in this time we have all the everything is random, all the numbers are random. So that's why we are using this method fit one cycle, and we are not using the fine-tuning method which we have been using in previous cases of transfer learning. Now, the first thing we can do to make this model a little bit better is to force those predictions to be between 0 and 5. Okay, we want to predict, so of course we want the ratings between 0 and 5. And for this we need to use sigmoid range. We are just changing this line of code, I guess. We are also providing y range over here. So y range basically will give us a range between 0 and 5.5, okay, to 5.5. And after that we will use the sigmoid range and provide the activations, I should say the predictions, as the first argument, and provide the y range, this range 0 to 0.5 as the second. And why have we used star? I don't get it, why they used star over here. Let's run this code anyway. I came across this syntax of star previously as well, right? But I couldn't find what exactly it means. Let me try to find it again. I want to know what is star, what does star self means in Python class. I don't want to know the use of self. I want to know what star self means. Try to Google it. DuckDuckGo doesn't give reliable answers most of the time. What is the use of star? I don't want to know just the use of star. I want to know the use of star self. This thing. Star self. What does it do? Maybe this article contains all the use cases. Okay, asterisks for unpacking into function call, for unpacking arguments given to a call, given to a function. Okay, this blog post does contain all the use cases. Okay, yeah. All right, and so this basically does the unpacking like this, fruit, zero fruit. But in this case, it was a list. In our case, it's a tuple. It's a tuple. And let's search. Does the sigmoid function look like? Sigmoid range. Okay. I get it now. So we don't we have to provide this individual arguments low and high, and we have a tuple which contains the values low and high. So this star basically unpacks that tuple and provides this individual arguments. Good, now I get it. And we have our sigmoid range applied model now. Let's get the model again. Dot product. We are passing number of users and number of movies and 50 latent factors. Get learner inside learn variable. Learner. Pass it the data loaders. Pass it the model as well, and the loss function again is MSE loss flat. Now we fit it for one cycle. We use the fit one cycle method to fit it for 5 epochs, and we pass 5 e raised to minus 3 as the learning rate. We got the results, and I guess getting the sigmoid range, I mean the ratings between 0 and 5 doesn't really affect the model results that much. This is reasonable start, but we can do better. Yeah, one obvious missing piece is that some users are just more positive or negative in their recommendations than others. And some movies are just plain better or worse than others. In our dot product representation, we do not have any way to encode either of these things. Okay, what do they mean here? is that some users are just more positive or negative in their recommendation, and some movies are just plain better or worse than other. Yeah, of course, of course. Suppose a user, you know, provides a positive, like is a push through kind. He likes all kinds of movies and provides positive ratings to all the movies. Or so suppose let's say a movie contains, regardless of its genre or anything, it contains uh, better ratings for all from all the users. So it doesn't matter if that user likes or dislikes those kind of movies. So this kind of thing is not being captured in this model. They are saying that basically. But in our dot product representation, we do not have any way to encode either of these things here. And if all you can say about a movie is, for instance, that it is very science fiction, very action oriented, and very not own, then you don't really have any way to say whether most people like it. Yeah, exactly. So this values are just, the attributes for the movies. We don't have a particular attribute which says that if that particular movie is likable or not. We should have one more factor which says that if it is likable or not. And same for users as well. You can say if that user is more positive or negative in his or her ratings. That's because at this point we only have weights. We don't have, okay, so that's where the biases comes in. If we have a single number for each user that we can add to a score and ditto for each movie, that will handle this missing piece very nicely. Oh, that's beautiful. So first of all, let's adjust our model architecture. So we are only adding this new factor, user bias and movie bias. So it's also an embedding of number of users and one. It's just one column. Movie bias is also just one column, and we are adding that bias, user bias. So this will select the rows on the I still don't know how this forward function works. Function, or I should say the method. I might have to research into how this function exactly works, because the author is not really providing the details of how it is implemented. Maybe it is PyTorch specific, like what PyTorch does behind the scenes. Or maybe I missed the points earlier, some points. I might have to re-review this again, I guess. Okay, let's get this model now. Yeah, I'm not going to write this code. Let's just copy it. Yeah, exactly. It is getting worse instead of being better, at least at the end of training. Why is that? If we look at both training carefully, we can see the validation loss stopped improving in the middle. Okay, validation, yeah, it is 869 and started to get worse. It stopped improving, like it flattened at 80.86 for 2 epochs, and that it started to get worse, 0.89 and so on. As we have seen, this is a clear indication of overfitting. In this case, there is no way to use data augmentation, so we will have to use another regularization technique. One approach that can be helpful is waiting. So watched the I have watched the course up to this topic only. So I have not gone through the videos of weight decay, this regularization techniques and so on. So after I have gone through that part of the course, video course, then I will get back to this notebook and we will start reviewing from weight decay again in the next stream, probably, maybe. So I have reviewed up to this much. We will stop this stream at this point and I will see you guys in the next stream. Bye bye.